Hey everybody, welcome back to the second to last episode of biostatistics. Today we'll be continuing to talk about regression. Specifically, I want to cover estimation and multiple regression, which is regression with multiple variables. So this is our world as we know it. Regression analysis, we've assigned a linear process to the mean of a distribution that generates our data. And thus far, we've assumed that our response variable, also called the outcome variable, is normally distributed with some mean that varies by observation. It doesn't mean that we estimate a separate parameter for each observation because what is in red is estimated. So although we observe n data points, I know I have 4 plotted, but suppose there's 4,000 there. The process that we have specified, process that we have proposed, we only need the intercept, the slope, and the sigma parameter. So only 3 things estimated no matter how many observations you have. Now, if you had 3 observations, you could not fit this model. You need more observations than things to estimate. But with 4, you could, actually. So I actually have not talked about estimation, so this is as good a time as any. So the first sort of way that regression analysis is presented, the first method of estimation is called least squares. Sometimes it's called ordinary least squares. But least squares is a family of ways to estimate this red line. What we're going to do to visualize, our predictions lie along the line, right? So the predictions are on the line. And they could be good, bad, something in between. So we have missed this observation. In fact, we have underpredicted this observation by how much? This much. This is the first error. And we could even write it out. This is our observed data point minus the predicted data point, which is mu1. Sometimes you will see it written in terms of an error. I'm trying not to introduce a lot of new notation. Our predictions are just the mean at x equals to 1. So our error is then y minus mu. It's greater than 0. Right? Because y is greater than mu, so our error is going to be greater than 0. Moving right along, we have overestimated this next point. Here is the second error, or we can also write it just like this, y2 minus mu2, and you can sort of see where we're going with this. So the least squares method of estimation says that we will pick values of alpha, beta, and sigma such that the sum over all observations of yi minus mu I squared is as small as possible. So we're going to pick, I'm going to just color code because red means estimated. We're going to pick values of our 3 parameters to make the sum of squares, right? That's where the square moniker comes from. the sum of squares, the sum of what? The sum of all of my observations, as small as possible, least squares. So the sum of squared errors, as small as possible. Another way to think about it, make the sum of squared errors as small as possible. And of course, you can see that this line that I have is pretty close to the best fit line. It minimizes the sum of squared errors, and it's certainly not, say, this line. Because for this flat line, this is bad fit. This line right here, we would penalize ourselves, and rightfully so, quite badly for these errors right here. Maybe these errors would increase only a little bit, but these errors on the end would increase quite a bit. And we do have this square term there to make sure we don't miss any data point by too much. So certainly not this bad fit line. So our software will pick alpha, beta, and sigma to be something like the line I have to make the sum of squared errors as small as possible. This is another way to write it. Okay, I want to present it a slightly different way, which gets into our data generating process. Because with these sum of squared errors, I actually didn't talk about the distribution at all. The distribution is very important. So, you know what? I'm just going to have to redo my observations. The distribution is very important because it might be implicit here in introduction to biostatistics, but it becomes very important later on. So what is really going on by saying this statement right here, they're saying that there's a normal distribution centered at some mean with a standard deviation of sigma, means that at my first value of x, I'm going to center a normal distribution right at this red line. And why do I say center? Because we know in a normal distribution, the central point is the mean. Right, and then that right there is mu1, our first prediction. And then I go on. So we take this distribution. By the way, the standard deviation is sigma. The standard deviation is sigma. Remember, sigma is just the average distance of data to the mean. So in our case, we want it to be as small as possible. We want this best fit line to be closest on average to the data. So then we take this normal distribution, we're just going to slide it up this red line. So then at the second value of my explanatory variable, I'm going to center a normal distribution that is equally wide. The only thing that changes is my mean. That should be a straight line. All right, this is my mu2, and so on and so forth. There's actually a distribution right there as well, and a distribution right there as well. So the next estimation method pays very close attention to the distribution from which our outcome variable comes from. And it's actually called maximum likelihood. Now, this can be quite mathematical, so I want to focus on a conceptual kind of visualization of it. So this says, pick values of alpha, beta, and sigma, right? Red means estimated, such that the height of the normal distribution at every data point is as tall as possible. So this is trying to make something large, as tall as possible, as large as possible. The least squares estimation is trying to minimize the sum of squared errors. Maximum likelihood estimation says, I'm going to fit these normal distributions using this alpha, beta, and sigma to make sure that the height of the distribution, especially the sum of the heights, I'll be even more specific, the sum of the natural log heights. The sum of the natural log of the heights is as large as possible. And you can see that it's actually saying the same thing, because the closer we are, the closer this line moves to my data point. Pretend it's not there, pretend it's here. You see, my error became small. Now my error is quite small. We're happy about that. And the height of this normal distribution right? That's the height of the normal at y1 is as large as possible. And so we pick these three parameters to make sure that the sum of the natural log of the heights across our entire data set is as large as possible. So this is actually much more general than least squares. Much more general. And you are much more likely to see it outside of our class when we start to deal with data that, where the response distribution has to be positive for counts, where the response variable has to be between 0 and 1 for probabilities. It becomes very important what distribution we assume our response variable came from. And the least squares can get us in trouble because we can start getting negative counts, we can start getting probabilities that are below 0 or above 1. So two different ways. They're actually equivalent. So maximum likelihood, sometimes you will see it as ML or MLE. More recently, machine learning gets in the way of this. So just make sure which ML people are referring to. Maximum likelihood is equivalent to least squares only if the distribution is normal. not so otherwise, and maximum likelihood will be a lot more general. So when you are looking at your SAS output and it says, well, here is the likelihood achieved by the model, it's giving you this sum of these heights, the sum of the natural log of the heights across all of the data points. And so with this maximum likelihood, with the likelihood, larger is better. Better fit for the model. For the maximum likelihood estimation, larger is better because our best fit line is closer to the data because the data has a higher height at that particular location. This brings me to the next point. Okay, for the likelihood, larger is better. But as we're starting to move into multiple regression, the question is, but how do we compare models where we have 20 explanatory variables in one, 20 predictors in one, and 2 in the other? How do we compare models like that? One of them can even fit better. But the question becomes, does it fit so much better that we can justify trying to estimate 18 additional things to achieve that slightly better fit? So the question is, and it's tied to this maximum likelihood. The question is, given that with maximum likelihood, larger is better because it indicates better fit, how to compare models with different explanatory variables. And this could be different explanatory variables, but the same number of explanatory variables. This could be different explanatory variables and different number of explanatory variables. I may have misspoken there. Different explanatory variables, same number of explanatory variables, or different explanatory variables, different number of explanatory variables. The answer is we use information criteria. These information criteria, there are many, and what I'm talking about is AIC, BIC, AICC, but there are many, many others. Many, many others. Our information criteria penalize the overall model fit for using additional explanatory variables. So what these information criteria allow us to do is to say, if I can get almost the same raw goodness of fit with fewer explanatory variables, then my estimation task was easier, and I should be rewarded for that. If I got almost the same fit with, say, 2 variables that another person got with 22 variables. So with this information criteria, it takes the likelihood and it assigns a penalty based on how many things we had to estimate. So, a very detailed dissection is outside the scope of this class, but it is very much dependent on the likelihood of the model. We must be fit to identical data. So you have to watch out for missing data, right? If you are trying to pick some explanatory variables and some of the explanatory variables have one observation missing, you're no longer comparing models, different models fit to the same data. And I will just make a recommendation. Use the corrected, the last C in corrected is the, sorry, the last C in AICC is corrected AIC. AIC stands for Akaike Information Criteria. BIC stands for Bayesian Information Criteria, though it is not Bayesian. AICC stands for Corrected Information Criteria. That's the one you want to use. Use the corrected information criteria. Sometimes it'll be a capital C, sometimes it'll be a little c, because it works well in large and small data sets. That is not the case for the AIC, and the BIC has its problems. In fact, I'm telling you to use the corrected AIC because the uncorrected AIC tends to select models that are too large, and the BIC tends to select models that are too small. So the AICC sort of takes that middle road and selects the correct model more often than the other two. Now, most often you will see all three presented. My recommendation is use the corrected AIC. Smaller is better. The magnitude is meaningless. So you are only using this criteria to compare different models, for which one does not overfit your data, does not estimate too many things for what you need. Okay. I will stop on estimation right there and move into, now that we've talked about selecting models with different covariates, how do we interpret models with different covariates and different amount of covariates? Okay. Most software should output information criteria. These tend to be pretty darn standard. So as I'm erasing, I'm going to have two sort of placeholder variables. Our interpretation and visualization will depend on whether our explanatory variable is quantitative or explanatory variable is categorical. And when I say categorical, it has two levels. It's some 0 level and a 1 level. So the first model we're going to go with is 1 categorical, 1 quantitative variable. I'm talking about explanatory variables. We know that we're actually manipulating the mean. Manipulating, or in other words, we are parameterizing the mean. So just to bring this full circle, we're still in the same world. But we're now going to have a lot more fun with this mean right there. One categorical, one quantitative. My mean is looking like this. I still need an intercept. To that intercept, I'm adding a beta for the quantitative. Okay, this is the coefficient for my quantitative explanatory variable. And I'm also now adding coefficient for the categorical variable times the categorical variable. So now my regression model has intercept, coefficient for the quantitative, coefficient for the categorical, and the sigma. I have 4 things that have to be estimated. So I need at least 5 data points, but hopefully a lot more than 5 to fit this model. What we're thinking about is that, notice that this right here is a common slope with respect to our variable q. And of course, a slope with respect to the categorical variable doesn't really make sense. And what we're thinking about here is this is a separation between the 2 groups. So what we're going to have is 2 parallel regression lines. Here's my y, here's my q. When my categorical variable is equal to 1, that mean, and my regression line therefore, and I'm just going to use break my color coding just for a sec. When my categorical variable is equal to 1, this would be my regression line. And so if I combine beta times 1 is just beta, if I just combine these things together, I have alpha plus beta c plus the slope times my quantitative variable. So it is then clear that this coefficient, beta c modifies the intercept. To complete the loop, when my categorical covariate is 0, well, mu sub I is alpha plus beta q times q plus beta c times 0. But anything times 0 is just 0. And so what we are left with is just our original regression line. So I have 2 regression lines. One of them has the intercept of alpha. The other one has the intercept of alpha plus this beta coefficient. This is the beta coefficient for the categorical term. So this right here is alpha plus beta categorical. Let's pretend that the slope is positive, and so, but notice that the slope is the same in both regression lines. So I have something that looks like that. The top is where my categorical variable is equal to 1. The bottom is where my categorical variable is equal to 0. And all along my values of my quantitative variable, the two regression lines will be separated by this coefficient. And the slope will be the same. Beta Q. It's the common slope. That's the world that we propose when we fit one categorical and one quantitative variable. Let's talk a little bit about interpretation. What we usually say is, for beta Q, we say that this is the expected unit change in the response, in the mean of the response, per unit change in Q adjusted for C. So sometimes you will say that you will lead with this. You will say that adjusted for my categorical variable, this coefficient is the expected unit change in my mean response per unit change in my quantitative variable. Sometimes you will say, here is my unit change controlling for. Sometimes you will say controlling for the other variable, and vice versa. You will say that beta C is the difference between our two categorical levels adjusted for whatever your quantitative variable is. And you can see that the slope is common, but the two lines are just forever separated by this beta coefficient. Okay, moving right along. That's one quantitative, one categorical. The next one is two quantitative variables. All right, we're still manipulating the mean. So here is my mean that will go right in there. I need an intercept. I need a beta Q1 times my Q1 sub I plus, let's go with the red plus, beta Q2 second quantitative variable. So I don't have a categorical variable anymore to do my trick of, I have two parallel regression lines. I instead have two quantitative variables. So with two quantitative variables, I actually have a plane. A plane, think a sheet of paper that is tilted in different ways. So I will attempt to draw in 3 dimensions now. It's always a very exciting event. Here is my response. Here is my first quantitative variable. Here is my second quantitative variable. This plane, think just a super flat, perfectly flat piece of paper, it hits our vertical axis right at alpha. Right, that is where both of our quantitative variables are equal to 0. Together, jointly. And now, from this point on, the tilt of that plane is going to depend on our slope with respect to the first quantitative variable and our slope with respect to the second quantitative variable. So, it looks like that. Along this axis, I have beta Q1. And now along this axis, I have beta Q2. So beta Q1 is the slope with respect to the first quantitative variable, and beta Q2, of course, is the slope with respect to the second quantitative variable. Intercept is where that plane hits that vertical axis. When we are, and of course that, we can have, this can rotate and tilt down in one direction and up in another direction. The way I drew it here, the way this is drawn, both beta Q1 and beta Q2 are both positive, but that doesn't have to be that way. One can be flat, right? Here's my plane. One can be flat and tilted here, and now I can tilt it here as well. I can tilt it down without changing the tilt here, and then change the tilt here. So this can rotate freely. The interpretation, beta Q1, expected change in the mean per unit change in Q1, all right, that's the slope with respect to Q1, holding the other variable constant. That's the formal definition and interpretation of this coefficient. It's the expected change in the mean per unit change in Q1, holding the other variable constant. By the way, what happens if you add a third quantitative variable? It becomes a hyperplane, and I cannot draw that for you. Cannot draw a hyperplane because it's in more than 3 dimensions. But so you would then do expected change in the mean per unit change in your variable that it's the slope with respect to, holding all other variables constant. Here we just have one, we can say holding the Q2 constant. Notice it doesn't matter what we actually hold it constant equal to. It's customary that set Q2 at the mean. In fact, that's what SAS does. It estimates it provides you with this a much better looking picture of a plane, and it holds all of your other covariates that are not part of this plane constant at the mean, but it doesn't actually matter. It doesn't actually matter. Another way to write it would be adjusted for Q2. Beta Q1 is the expected unit change in the mean with respect to Q1, your first quantitative variable. Okay, we went from just a single regression line or a t-test. Then we went and combined a quantitative and categorical variable. We got two parallel regression lines. Now we said, okay, what if I have two quantitative variables? I get a plane. Well, it's natural to say, well, what if we now add to this a categorical variable? What if we now add to this world a categorical variable? So the world becomes one categorical plus two quantitative. Okay. I'm going to go and do beta C times C sub I. I'm going to rewrite that because you can't see it. Beta C categorical variable. That's much better. So if we're going to count, we're still just manipulating the mean that will go into this normal distribution. It will vary with each observation, right? Track my sub i's, because I've made this quantitative measurement, I made this quantitative measurement, I made this categorical measurement as well. I'm now estimating 1, 2, 3, 4, 5 different things. I need at least 6 data points, but hopefully much, much, much more than 6 data points. So you can sort of imagine what's going to happen. Now I have not one plane, but I now have 2 parallel planes. Cool. They are now 2 parallel planes separated by, at all points, this beta C coefficient, because I can write out the equation of each plane. So where the C is equal to 1, my plane. Why is that a plane? Because I still have 2 quantitative variables. When I fix my categorical variable at 1. All right. And when my categorical variable is 0, whoops, if it's 1, I need to add beta C. If I fix my categorical variable at 0, alpha plus beta Q1 plus beta Q2 plus beta C times 0, right? But put 0 in for C. This term disappears. This term just becomes beta C. Here is my new intercept. So pretend that beta C is greater than 0. So then from my old intercept, I need to shift upwards by this coefficient. And right there, I will have a perfectly parallel plane, such that this is the plane where C equals 1. This is the plane where C equals 0. But these two slopes, with respect to the second quantitative variable, are identical, and the two slopes with respect to the first quantitative variable are identical, right? Common slope, common slope, common slope, common slope. What happens when I increase this to 3? I can no longer draw that for you guys. And no longer draw it for you. Because now this is a hyperplane. And I haven't yet learned how to draw in more than 3 dimensions. Can't do it. All right. And as I mentioned before, when you're computing these, you can look at your information criteria and determine, do you need to go to 3 quantitative variables? Can you get away with just 1 categorical, 1 quantitative? Do you need 2 quantitative variables? You can also then look and see if each one of these coefficients is significantly different than 0. Those are 2 different questions. A coefficient could be significantly different than 0, but the AIC could still select that model. So remember, each one of these has its own confidence interval, 1, 2, 3, 4, 5. And in fact, the alphas and the betas also have p-values. So we can determine, for example, if our 2 planes are statistically significantly separated. Or if they're not statistically significantly separated, can we get away with just 1 plane? If this beta C is not statistically significantly different than 0. Let's go through a quick example. It's birth weight again. But it's going to be a little different. It'll be using the same data set as you guys played with that came from our collaborator. And so feel free to follow along in SAS. So if I have 3 covariates, in fact, I will now have my last case. I will have 2 quantitative and 1 categorical explanatory variables. My outcome variable is going to be birth weight, so that's a little different than what we did during the activity. Birth weight in kilograms. You have to keep the units in mind. You have to keep the units in mind. Remember, all the betas are interpreted in terms of per unit change in your explanatory variable. The expected change in the response per unit change in the explanatory variable. So what we have then is, I don't touch this, this stays the same. I'm assuming that birth weight is normally distributed. And then my mean is, in terms of Greek notation first, alpha plus. I have maternal age. Plus, I have gestational age. As you're writing this out, guys, be careful and don't put the subscript on the coefficient, right? Then you will be estimating as many parameters as you have observations. Right now, we're estimating a single parameter as this mom age is changing. Gestational age plus my categorical variable, it won't be delivery type, it will be whether there were multiple babies. So it's going to be beta multiple. And this multiple categorical variable, right? Mom age is the maternal age, just age is the gestational age. So this is in years. Mom age, gestational age is in weeks. Remember, I said to keep careful eye on the units. And multiple is 1 when multiple babies were born during the same event. Okay, so I have the last example, right? I have two parallel planes. The planes, the axes, right? The axes of the parallel planes are defined by maternal age and gestational age. These are two quantitative variables. And my two planes will be separated by beta multiple. I'll now plug in the estimates that I got for my, there it is, negative 3.84 birth weights in kilograms. Beta for maternal age is 0.006. Beta for gestational age is 0.176. And beta for multiple is, and I'll erase the plus sign because it's actually negative 0.162. All right, a couple of things to look at. We have a negative intercept. But how could that be? Our outcome is birth weight in kilograms. Clearly, the birth weight cannot be negative. But what does this value represent? That's the value where all of our remaining explanatory variables are set at 0. Maternal age is 0, gestational age is 0. Maternal age can't be 0 and gestational age can't be 0. So this intercept is uninterpretable, as most intercepts are. Number one. Number two, it's fair to ask, man, this is a small coefficient. Is the coefficient statistically significantly different than 0? Is beta mom age different than 0? Well, I can look at the p-value that tests the hypothesis that it's equal to 0, but better yet, you can record the 95% confidence interval, CI for confidence interval, and it actually comes out to 0.002, 0.010. All right, we exclude 0, therefore is statistically significantly different from 0. Very good. But still, it's such a small number. But remember, this is per year. So could the unit have something to do with it? Well, but wait a minute. We have weeks. Gestational age is measured in weeks. But we can convert years into weeks, could we not? To convert years into weeks, we would divide this coefficient. To convert years into weeks, we would divide the coefficient by 52, making it that much smaller. But we wouldn't change the statistical significance, by the way, because we would just divide everything but by 52. And then if we did that, then this tiny number will be the expected change in the mean birth weight, population mean birth weight, per additional week in maternal age, adjusted for the other covariates. So the way I have it now, 0.006 kilograms is the expected change, that increase in population mean birth weight per additional year of maternal age. If you wanted to put it on the same scale as the other coefficient, you would need to divide it by 52. And you're allowed to do that. Although it doesn't make that much sense to record maternal age in weeks as much as it does gestational age. Okay? We are assured that it matters, at least from a statistical standpoint, because we have determined it is statistically significantly different. Does it matter from a practical standpoint? Boy, I would doubt it. I would doubt it. Probably doesn't matter from a practical standpoint. Definitely matters at the 95% confidence level from a statistical standpoint. All right, moving right along. We have now covered the intercept and beta maternal age. We're moving on to beta gestational age. And so each one of these is adjusted for everything else, right? So the other way, and I'm going to model a few ways of interpreting these things. So I will just start with the statement about adjusted. I'll say adjusted for, now I'm interpreting this one. Adjusted for maternal age and possible multiple deliveries, multiple babies, we expect the birth weight and more specifically the population mean birth weight to increase by 0.176 kilograms on average. When people write on average, they mean that we're talking about the population mean that will go into this normal distribution from which the actual birth weights will be generated. Adjusted for maternal age and possible multiple babies, we expect the birth weight to increase by 0.176 kilograms on average per week of gestation. Per week of gestation, about just under a fifth of a kilogram, adjusted for maternal age and chance for multiple deliveries. What about per day of gestation? Per day of gestation, 0.176 divided by 7, because there are 7 days in a week, just like there were 52 weeks in a year. Can you compute this per day as well? You certainly could. Knock yourself out. Is this statistically significantly different than 0? You betcha. In fact, the 95% confidence interval for gestational age is 0.17 to 0.181. And this is what I say, that the confidence interval is so much more useful than a p-value, because look at how precise. Look at how precise we're estimating that slope, that growth. So, the degree of growth per additional week of gestational age. It's between 0.17 and 0.18 kilograms, right? That's our plausible range of values. 0 is well outside the range, but it's also such a precisely estimated parameter. It's a thing of beauty. But our sample size was 1,800, and we're just estimating 5 things. We shouldn't be too surprised that we're getting this precise of an estimate. So this gives us an idea of how much our baby's going to grow per week of gestational age, adjusted for maternal age, and whether we're having multiple babies. Moving right along, those are our 2 quantitative variables, adjusted for one another. All right, the slopes of our planes. Remember, we're still dealing with two parallel planes tilted by this and that, separated by our multiple babies. So, controlling for, remember I said I'm going to model different ways of interpreting. Controlling for maternal age and gestational age. When multiple babies are born, infants, so when I say when multiple babies are born, I'm doing the categorical variable is equal to 1, right? I'm setting this equal to 1 when I say when multiple babies are born. Controlling for maternal age and gestational age, I'm saying keeping these things constant. When multiple infants are born, birth weight tends to be not causal language. Please pay attention. Causal language. Birth weight tends to be 0.162 kilograms lower than when a single baby is born. Adjusted for maternal age and gestational age. When we get multiple infants born in the same event, the birth weights tend to be 0.16 kilograms lower. Lower because we get a negative number, and that 95% confidence interval also comfortably excludes 0. So all 3 of our beta coefficients are statistically significantly different than 0, but I think it's fair to question how much practical importance maternal age has. If your prior research suggests that maternal age is a super important covariate to adjust for, put it in the model and don't worry about it. If you run 37 models and you compare each one of them using the corrected AIC, go ahead and go with the model that has the lowest corrected AIC, unless it is a complete nonsense model. Let science drive your decision, please. I'm done for today. Thank you for listening. We have our second to last activity coming up. I hope you're all well. Good night.